there are bios in the documents that you all should have been given for everyone, so I won't elongate the introduction. If you all do not know Professor Luigi Di Sarno yet, something is wrong with you as engineers. Yeah. Professor Di Sarno is a lecturer at the University in Naples, Liverpool, and I'm probably missing a few as well. Today he will be speaking to us about design standards, past, present, and future.
Thanks, Omar. Thanks for the nice word. And I've been given today a very challenging task because I have to go back 30 years in 30 minutes. So I hope I can do that. So I had enough coffee, I hope. So what we will start with is primarily focusing on the seismic design. So we start from key questions that I'm trying to address during this presentation. And firstly is the how and why has structural seismic design changed in the last 30 years? There have been a number of changes, and I'm trying to focus on those that they really have an impact on the practice. Then the second question is, why is the current seismic design code, and which is the most appropriate use that is currently based on? And also more importantly, yes, thank you very much, is what are the challenges that we are going to face for the next generation of seismic design code? So 3 questions, 30 minutes. Where we start from? I think we should start from a very important type of failure that started when I was born, 1971, if you want to know my age. And we had, for example, University of Southern California, Olive Hospital, that was affected by a very significant earthquake that was in 1971, San Fernando earthquake, and there was a collapse of this building. And the reason why I'm showing this specific building is because this is a critical facility. It was an hospital. The building was stiff enough on the top part, but was weak enough at the bottom side. And typically, for example, there's been a belief that structures which had soft story could behave better. That was Corbusier's invention, for example, flexibility. But flexibility does not always work. In fact, this building collapsed, but also is very interesting to mention that after this building, there's been a very heavy change in terms of regulation in US. This is the US context. And what has happened is that when there was the next large earthquake in US, 1994, Northridge, this building was also affected by a strong motion. And what happened is that the superstructure behaved well, so there was no structural damage. Unfortunately, all the building content collapsed. So still the building was not usable, which means that when we look at structural engineering, we need to consider not only the structure as an important feature for its functionality, but also, and more importantly, the building contents, particularly when we look at hospital. And this is something that we should consider these days for the next generation of codes, which should go beyond the structure response. Now, next, in terms of response of structures, again moving from early application. For example, before 1994, there was the typical approach, no ductile base, so there was no capacity design enforced in seismic design. And in fact, in 1994, again, Northridge earthquake, which also had a vertical component, very severe, showed that details on bridge piers, as shown here, for example, were not effective. And in fact, all the bars buckled, but also more importantly, looking at infrastructure, we are discussing these days of resilient infrastructure, they were not resilient at all. In fact, actually what was mentioned, observed during this earthquake is that after the 1971 earthquake in San Fernando, part of the California was subjected to a retrofitting program, and all infrastructure that were affected by the retrofitting program were not damaged, while all the others, for example this one, had severe damage. And severe damage was observed for decks in bridges, but also, and more importantly, this is part of the rethinking of all the seismic design for steel structure, happened and to beam-to-column connection, where material, for example, were not enough ductile, they were brittle enough to create large cracks, particularly for large columns and large beams and small columns. And this, of course, changed all the next generation since then for codes. What has happened recently? In 2023, February, there were two major earthquakes at the intersection between three faults area, which are at the Turkey-Syria border. And I had the pleasure also to go there soon after the earthquake. The earthquake occurred in February. We went there to survey most of the building in May. And what we observed is that, again, another part of the world, we are moving here in Europe, actually at the border with Asia, we observed that through the years, starting from 2007, where a number of buildings were affected by large earthquakes, and they also generated the design to be changed in some part of the Turkey, but still damage was observed for those buildings that were whose design was based on such code. Then, for more modern type of buildings, the damage was limited, and what we observed. After checking also the response of the building on the superstructure, but more importantly, looking at the content, is that a number of hospital buildings that were built there after the code of 2018 that has enforced for the first time in Turkey the compulsory use of base isolators for all hospital buildings, there was no damage at all. So all the buildings, hospital buildings in Turkey, were able to survive this earthquake. And this earthquake is a 7.4 magnitude, so it's a very large earthquake. So it means that we have now the tools, we have the technology that will allow us to survive even after a major earthquake. And the structure can be built resiliently, but also more important, in a sustainable manner, because if there is no damage in this type of structure, it means that we need not to build from scratch. So the resources are still not being used, and we can preserve our nature. Now, moving forward, and this is basically what we are going to discuss in details here today. These are the number of codes that have been changing themselves, updating themselves, because of what? Because of lesson learned from previous example of earthquake, the previous example damage that has been collected after major earthquakes. And here I'm starting from UBC 76, which really dates back before the target of this conference, which is 1994, but this is to show that there's been a change in the mindset of how structures have been designed in seismic area. And more recently, there has been also a push towards the use of reliability to make the structure safer and safer. And what I mean safer and safer, we have been more and more demanding in terms of limiting, for example, interstory drift. We have been more demanding in terms of protecting components that are fundamental for the functionality, particularly of critical infrastructure, like hospital, like nuclear power plant, or any other type of structure, for example, museums, and that are very important. We are working, for example, these days on protection of status through base isolation, because you want to preserve them from the failure. What is very important to note in this diagram is that there has been also a change of methodology because of the knowledge that has been acquired, as I said, after major event, and the change from a low stress design to LFRD that has been instrumental for the use and implementation of capacity design. And also, more importantly, I would say the change in terms of selection for the input. We have been discussing previously with Tony Gibbs through the change of spectrum, and also through Elias that showed us how this has been computed for this area. But more importantly, it's been based on the change of code approach that has now been used in US, in combination also with methods of analysis through which engineer can handle and can limit the damage into structure, like, for example, use of modal response analysis, which is becoming very common these days, but also, more importantly, I would like to stress, since we mentioned about soil, the effect of soil structure interaction, particularly on landmark structure like tall buildings, like offshore structure, and so on. And I will also conclude this presentation with some details that are now implemented in code of practice that have changed through the years. Now, why I'm showing this paper? Because I think this is one of those seminal papers, again, available for free, as Tony said, online, but it is only 9 pages a paper. Is very important because it contains the change of the approach for codes. And these are summarized in these 2 squares here. Because these days we are relying on LRFD, which is only part of the more general approach, which is probabilistic approach. And this is really where we should go in the future, because we need to weight differently the structure depending on the use, depending on the contents. So you see here three different levels of approaches that can be implemented in the code. This is a paper by Galambosch that promoted, along with Eliggenhood, this approach in the United States and then spread around the world. And they looked at three different levels. The level one, which is based on what we do in the design office. Typically, we have simplified approaches that come from a higher level approach, which is, in this case, named as second level approach, first order, second moment, which is looking at the reliability of the structure. So really, we want to know what's the safety, the inherent safety of the structure based on probabilistic analysis. And more importantly, if we expand this, we include both on the demand side, but also on the capacity, weighting also the safety factor through the confidence value, we will get the full probabilistic methods. Of course, this level seems to be too advanced, but it is nowadays widely used by insurance, for example, because it's the way that we can even combine different hazards. That's another important challenge for the next generation code. How you combine, for example, earthquakes with wind, with flood, with other natural and also technological hazard, whichever is called NATEC. And you can only do that by considering the approach based on probabilistic analysis. And these are the way these type of approaches are implemented these days in code of practice. So nothing new, but really a way to move from ASD, a global stress design, to LRFD that has been beneficial. And that has also brought us to more sustainable type of structure, because the structure tends to behave this day lighter and lighter, more flexible. But flexibility should also be designed accordingly. For example, for non-structural component, like for example, windows and all the building contents. Now, just few reminder that even the fundamental approach based on two quantities, which is the period and the base shear, have changed through the times. Why? Because the architect, because the engineer have come up with different solutions for lateral structural system. So it means that there has been acquisition of data on site, and in fact you see here some comparisons of the fundamental period, simplified, first rule of thumb, that you will find the code for identifying the fundamental period of the structure, hence entering the code spectrum and determining the action. And this was based on another seminal work of Chopra and Goel, 1997, as shown here. This is another available for free on the internet. And this is a report from Berkeley where you may find a number of a collection of data here of different structural systems. Here, MRF, moment resisting frame, buildings, and here what you have is the period of vibration versus the height, because typically the period will depend on the height, not only on the height, but typically that's the most governing parameter. And all these dots are collected from site, instrumented building, and this has been done also for reinforced concrete, moment resisting frame, and also for shear wall. And if you search in the literature, there are more and more data updated. This is both for earthquake engineering, but more recently, it has been done also for wind engineering. So if you look into, for example, the response of tall buildings, South Asia, you will find similar plot. These are very important for getting an understanding of the fundamental period. Even for vulnerability assessment, because you need to know the period to determine, for example, the likelihood of, for example, the seismic vulnerability or the wind low resistance. Now, other approaches related to base shear, again, you'll find here the evolution through the history, and more important, you see how, for example, new parameters have been introduced. These are pretty similar around the world. If you check, for example, different codes, this is the case of US, how it has evolved up to ASCE, American Society of Civil Engineers 722, you see that basically there have been the introduction of new parameters, in particular the R factor, which is what I call to my student, the discount factor, because really you are lowering down the forces, but to an expense, and the expense is the ductility. So you are not getting discount without then paying off, for example, your card in the supermarket. The same thing happens here. You get lower forces, but then you need to implement more seismic details. That's what we do currently in the so-called capacity design methods. The same applies also in Europe. Eurocode 8, this is the version 0.4 currently adopted, but also in the revised version is exactly the same. Now, the number here will change slightly depending on for example, the reliability of the system, and you will also find that more and more R factor have been added because, as I said, the flexibility of lateral resisting system, but more importantly, the number of solutions that have been adopted. If you think that nowadays there are a number of tall buildings that are in between for example, shear walls and moment resisting frame with and without BRBs. It means that we are going towards hybrid solution. So you will find this type of R factors implemented in a number of new codes, even in commentary, that are always very important as background information. But I would say that the most important change that we have been observed in the last 30 years has been based primarily on the change of the seismic zonation. Elias, Mr. Gibbs have given us a very complete presentation of what's going on here. I'm trying to make it the same in the US, but also in Europe. We've moved from, for example, the evaluation of PGA as a unique and scalar that could identify the seismic zonation for an area to even to the change of period, for example, based again on probabilistic seismic zonation or based on Poisson model and so on, where we moved from the typical zone classified as zeta factor to MC, massive credible earthquake. And this is also very common in Europe, where a recent study have shown that the same applies. You see some of the area, particularly in the south here, with Greece, with Turkey being one those of the most active seismic zone in the region, with a period of acceleration that goes up to 1G. Typically in Greece, you have between 0.4 and 0.6. You go to Turkey, you get up to 0.9, depends on the soil. There are some soil amplification that can be very consistent, very high. And also the same applies in Italy, where particularly along the Apennine, so this spine of the main peninsula, there are acceleration that can go as high as 0.6. Now, this type of acceleration can be low when compared to what happens in other parts of the region, other regions around the world. For example, here, I'm just simply with these slides overlapping what Mr. Gibbs said before, where there has been a recent study carried out by Pavia, 2010, with Walter Salazar, and this was the project that Mr. Gibbs has managed along with Gianmichele Calvi, and there has been the seismicity of the Eastern Caribbean based on different parameters, which is very important. So it has been based on PGA, ground acceleration, but also more importantly, to connect with the structural code with the two values, the corner period, 0.2 seconds and 1 second, that will allow us to use the spectral shape that is implemented in code of practice. And this has been also updated recently for Cayman Islands. Now, a few words about the shape of the spectrum, because this has been also gone through a number of changes through the years. Initially, we had a very simple type of approach, 1994, where there were only 3 soil, and you see the effect of the soil here that shows that the softer the soil, the larger the spectral acceleration, which is normal. That's why, for example, you tend not to build on a soft soil. But again, you can't prevent the developing those areas, so you are going to increase for larger period the design amplification. This starts to have a sort of more common type of modern approach in 1997, which really starts to be the change in US with the control point. And control point are these two that then will correspond later to the 0.2 second, 1 second, that are the 2 periods that were implemented for seismic design. Here we are. And more importantly, this is again the first one, we moved nowadays towards also a change in terms of rating period. Now, I want to stress this because I believe engineers will have, at the moment, all the tools, but they need to use them properly because we have a number of different scenarios being set, and we need to be sure that they are consistent with the seismic details as implemented in the codes. Most often, particularly, and I come from a sort of experience in Europe, but also being exposed in a number of projects here in this part of the region, sometimes they are not well matched. So there is a match of the seismic details that will comply with the capacity design rule, but when you look at the input, it's not exactly the one that you should design for, or the one that is the most suitable for the type of structure that you are designing. Hospital, for example, or a critical facility like power plant or refinery and so on. So please be aware that there is a close match between the reliability implemented in the input, in this case in terms of earthquake, and the seismic detail as prescribed in code of practice. This is something that engineers should also check to be consistent with their design. And again, some changes to go to move forward up to ASC 7 to 2005, where there are also some indication for the long period and short period type of approach. But this is part of what is currently implemented in code of practice. So nothing new, simply a comparison and an evolution in terms of spectral shape based on more data. Because at the base of all these studies, also for example in Europe, there have been a number of additional collection of data after earthquake, historically, but also because of the local seismicity, based on the evaluation of the soil response, and also other features that relates to the shape that is pretty the same around the world, but it has to be adapted because of this corner period, as I mentioned earlier. So, what is the current practice in terms of design? Now moving from the input towards the structural engineering. And it can be summarized in these 4 points that I have here on the slides. Firstly, and all the design are based on 3 parameters: strength, ductility, and deformation. Deformation really relates to design under wind, design under low, moderate earthquakes, but also when we move towards high magnitude, we need to look at the strength. We want to constrain within the yield point. It really depends on the performance we want to achieve, but also, more importantly, we need to comply with the life safety and collapse prevention. That's performance-based design, started in 1999, Seattle, California. Fundamentally used for limit the and to comply with the damageability limit states is stiffness. So structure should be stiff enough in order to prevent damage for recurrent or frequent earthquakes. Acceleration, that's something that is not really yet in the DNA of the engineers. What does it mean? We want to create functionality. For those of you that have already designed tall buildings, they mean that they know that this is a fundamental governing design parameters, a problem for high-rise building. Not always the case for buildings, where we look only at the story drift, for example, or at the story shear. Acceleration will create the comfortability of the building. That's very important, vertically and horizontally. So there are milli-Gs, very small values, but it needs to be not yet in many codes. Only in Hong Kong, for example, there's a code that overlooks at this specific type of performance parameter. And of course, if you look at the conceptual design, there is a mix and trade-off between displacement, acceleration, stiffness, and strength, which is not always very easy to comply with, because some of these are competing parameters, so it's very difficult. That's where the engineering is important to be included. And to show also the possible tools that we have, the possible approach that we can rely on, there are at least two ways of dealing with this type of design. One is the traditional one, relying on the so-called discount factor, R factor or Q factor, that reduces the forces because we want to allow for ductility, which means that our structure are going to be damaged after an earthquake. This is something that is clear for engineers, not always to the client, to the contractors, because they say, oh, you fail your design because after earthquake of 6.5, which is above the 5.5 included in code of practice, the structure failed. That's normal. I've designed for that type of response to occur because I've scaled down my input here. And of course, you get some damage at beam column connection, typically observed after any small, medium earthquakes because of the weak beam, strong column approach. And what are the alternatives? These days, we have alternatives, and those are based, for example, on vibration control, something that is not new in engineering, but has been taken from mechanical engineering. Even your dishwasher at home relies on this. And in fact, for example, or whoever is experienced with laundry, when you start with your laundering machine, what does it do? It starts to rotate, it starts to move, but then suddenly it stops because it has some control of the vibration. In that case, it's a sort of passive device applied on the system, on the centrifuge, which has a piece of concrete, typically, that is resting on it. That same things can be done for buildings. You can have a mass on top of building, TMD. You can have braces that are dissipating energy in buildings, particularly for retrofitting, very, very effective, but also base isolators that are isolating the structure from the movement that is generated by the ground. So you have a top structure moving rigidly and all the deformation taking place at a certain level, base isolators. And that's something that has been observed, not only computed, being very effective from Turkey, but also in Japan, in Italy, and so on, a number of other cases around the world that have shown that its effectiveness. Now, this is very interesting because it, in a way, compares the performance-based design methodology, 1999, so nearly 25 years old now, in earthquake engineering, now being adopted also for wind. I said before that we are going through harmonization of code. Harmonization means that the hazard, when the earthquake occurs, it doesn't know that there is a wind acting simultaneously, or the building does not recognize earthquakes or wind, just knows the actions. And this action can be even simultaneous. So basically, there is now a trend to use the same approach that we have been typically adopting in earthquake engineering since the early 2000s for wind design. And you see here the performance-based design can be extended also for the design of tall buildings, but also, I'm going to add, we're working on that, on flood. So the next generation of ASCE will include a third matrix that also will look at another natural hazard, which is flood, being very important these days in a number of countries around the world. So, and of course, there are also different methodologies being adopted. Since 2000, since millennium, there has been a methodology particularly adopted in Europe through the work of Nigel Priestley by Michele Calvi on displacement-based design. So typically, in seismic design, we look at the forces as primary design parameter. Here we are looking at the response of the structure. The structure does not really know forces. Forces is a sort of invention. You know, it's based on an idea that came from Cauchy, early 90s, so no, 80s. And what is really being observed after damage is the displacement. The structure is going to be displaced because of the deformation that is taking place. So there is now a paradigm shift between the acceleration response spectrum towards the displacement response spectrum, because we can design for an imposed displacement that is going to be acting on a structure, and hence we can limit the displacement based on the maximum allowable performance that we want to obtain for the given structure. And this is basically summarized in these slides, where starting from, for example, a building that typically in this methodology, which is displacement-based design approach, reverted of the current force-based design approach, we look at a structure, we simulate it as a single degrees of freedom, equivalent, probably is a 3/4 of the mass at 2/3 of the height, is a single degrees of freedom, very simple. They used to do by hand since 1971, Vulcan, Urbana-Champaign, so you don't need large computers to do that. But also you can then linearize the system. You know, that's very important. Sometimes we are not very familiar with nonlinear analysis. Here, everything is linearized, equivalently, of course. So what you do, and this has been done in the literature, we have relationship between ductility, high damage, with something that is still a sort of an invention, but is a way of tackling nonlinearities, high damping. And then we have curves that correlates ductility levels with damping level. And then what we can do, we can use the graph I showed you before, which is the displacement response spectrum, where by entering with a given displacement, because we know that the window has not to break, so it means that the interstory drift has to be less than 1.5%, and then we introduce this value as displacement limit of the single degrees of freedom at this level of the mass, and we get, for different level of damping, the period. So we design a structure with a given period. So we go back to our now office, and we can do any calculation elastically, SAP 2000, any other, even your own MATLAB-based software, and then you can come up with a structure that then is going to be checked for force base, and not the reverse as you do in current design approach, where you design for forces and then you check displacement. The process is inverted here. And this has been codified in this next generation design code by Michele Calvi and Priestley here. So moving ahead, I think I'm getting late, but I'm also getting close to the end. There is the whole big issue, the chapter of retrofitting, which I believe is the next generation of engineer. You know, this is the next probably century work. A lot of buildings have been already constructed. A lot of infrastructure have been constructed. They are aging. So what we are going to do from now onward is being, you know, we discussed this morning about climate change. I've heard in a few presentations. The structure are also going to lose their strength. They are going to lose their stiffness. Why? Because the cover is going to spout. Then there is the, for example, a heavy load fatigue. There are a number of aging effects that are eroding as human being. You know, sometimes you get age and you get not always young or fit. So unfortunately, so you have to go to hospital or you have to do some checks. I'm not going to say hospital necessarily, but at least you do checks. And checks means that you have to go on buildings, do a new assessment, and the assessment is going to take into account all the previous history. So it means that the concrete that you initially have selected as C2025 is now becoming 1822. How you do that? You need to perform non-destructive testing, you need to perform some destructive testing, you need to do some rebar assessment, for example, if you do not have the drawing. So there's a new area there that has been prompted by these needs. And what you do if the structure is vulnerable, then you start to apply retrofitting measure. In some cases, you are not allowed to go inside, because then you need to relocate people. Business interruption can be a very important aspect to account for. So you go from exterior applications. And hence, you can consider, for example, exoskeleton. Greek, sorry for my pronunciation. So it means that externally, you apply something that will retrofit the structure. So it's something that looks like this. And you will continue to use your structure by simply applying externally braces or walls or any other type of solution, or dissipators. Could be, for example, friction pendulum, or could be, friction devices, or you can even cut the building with the base isolators here. These are jacks. These are elements that will dissipate energy. What you have, for example, in the wings of airplane when it needs to stop during landing operation, and so on. So this is really new technology. And all this not started yesterday, but again, early, I would say, 1995 here, with FEMA 273, that was launched in 1997, and bring up to ACI 31 and 41, which are more recently being published by the American Code. You see here the evolution again, moving towards performance-based design engineering, where, again, you are going to retrofit your structure, which not necessarily need to comply with the new rules. You can also admit, that's what we do currently in a number of applications in south of Europe, in Italy in particular, to a percentage of the full new type of structure. So 80%, for example, 60%. Why? Because if these are governmental buildings, are you going to ask the Prime Minister to invest all his money for the next 5 years to retrofit all your building? He will say, no, I'm not going to do that. So don't even go to check them, because he doesn't want to tell people that hospitals are all substandard. So what you can do, you can allocate money in a smart manner so that you can prioritize your intervention. And then you can retrofit up to a certain level that is accepted by community as acceptable risk. So it means that you're going to invest part of your resources to retrofit the list.
Send me a screenshot of the alarm now.
I don't know. So probably that's governmental that's complaining. Anyway, so I'll move fast so that I will not get any more complaint. So these are also some of the application of base isolation, which is not only something that academics like me have been studying for the last 25 years, but have been in place since 1969. So these are older than me. And this is the first application in Europe, in Macedonia, Skopje, of unreinforced isolators that were used for this school. Now they're being replaced because they are old enough. So these are technology that at least they can last 50 years without any maintenance. So moving on, again, this is part of the base isolation seismic code. As Tony said before, everything is available for free on the internet, but this is just a matter of comparing them, which means that the philosophy around the world is pretty the same. So it doesn't matter which code you're using. They use pretty the same approach. It's important about the technology. And since 1997, base isolation has been introduced in ASCE, chapter 12, then it moved to chapter 11, moving forward, back and forth, depending on if it is classified under passive devices or more generally explicitly as base isolation. But it has been proved a very effective type of solution for retrofitting structure or for new buildings. Some of the design issue that relates to the structure. If we are going to design a base isolated structure, the design is becoming very, very simple. The top part is elastic, is rigid, so you don't need to do any calculation. The bottom part is a single degrees of freedom. So again, go back to basic structural dynamics. By hand, you calculate everything, the period, the flexibility, the number of isolators, and so on. And these are some of the indication how it has evolved through the years. And it is becoming even more reliable and reliable. So the engineer have had more confidence in reducing the level of, increasing the level of safety and reducing the penalty factors that were initially introduced in code of practice. And they also are aware nowadays of the aging effect of these devices, particularly if you are going to use them into infrastructure. These are the case, for example, that have been mediated from AStructE, where isolators have been used in harsh environment, icing, de-icing, rubber exposed to large type of cycle may age very quickly, so they have a lambda factor that are penalty factor to account that this system may age very quickly. And what's next then? Next is base isolation, also in Eurocode. That's something that has been then there since the millennium. But also, these are the technologies, and I'm going very close to the end now, that we have at our hands as engineer, where we can rely, again, either on traditional or innovative approach. What is changing is that when we deal with a traditional approach, we are increasing the capacity. Here, with innovative approach, we are reducing the demand. Why? Because we are making the structure far away from the input. Elias was talking about the frequency of the soil. If it is 0.5 hertz, 2 seconds, we are making the structure going longer or shorter. So it's keeping the resonance, which is very important. If there is no resonance, the earthquake is not really creating any damage. The damage is only occurring because of the resonance between the soil and the superstructure. And these are the approaches. Again, a practical example from exterior, exoskeleton applied on a school, and it worked for a number of reasons. The school was initially torsionally unbalanced. We can bring back the structure to its symmetry because we are going to act externally such that the structure is behaving now in a symmetric manner. You see here in strategic location these dot lines that correspond to the braces being applied. So these are part of the reinforcement, of course. Through the years, there have been more and more stringent type of requirement for the design. Why? Because we want to be sure that everything is going to happen as intended in design. Engineer design for control damage. So they want to be sure that what they have in mind is happening on structure. So they need to enforce and drive the failure to occur because earthquakes always know the weakest link. So these are requirements for steel. It's exactly the same because of the thickness, so the slenderness of the components are becoming smaller and smaller. So it means that the system needs to become more robust. So it means that we are going to act on local B over T, which are local reinforcement, or in this case, local buckling to be prevented. And this has been implemented in recent practice, for example, since 2016 in ASCI, American Institute of Steel Construction. And really going now to the last slides, I think. That's what happens in Europe, pretty much the same, with the controlling level of axial load, for example, in columns, because columns are very prone to buckle. So we want to limit the maximum axial load to 30%, for example, keep it low so they can dissipate more energy. And this drives me to the last part of the presentation. What is on the horizon? What you can see, beyond the fence. Earthquakes are always an emergency around the world. This has been shown recently also by the net loss catalog provided by Munich Re in Europe, and for a number of events around the world, showing the importance of earthquakes that have occurred in Europe in particular, in Morocco in September, then in Syria here. I think there's been a shift of these squares there. But more importantly, I believe that now we are going towards the next generation of design. And this next generation is implementing what is called holistic approach. We can't disconnect structure from the services. Services are more important than structure. This is not my study. This was a study that was published in 2003 by Miranda, Stanford, with Tagavi, and they've shown the cost breakdown for different type of system. And if you look, for example, a hospital, the cost of the structure is less than 10%. So if you are going to have a damage on the structure, you're going to lose very, very little. But if you are going to damage or experience damage after an earthquake due to no structural component, or even more importantly, to the building contents, you are going to lose nearly 90% of the overall cost of the structure. So what is very important for the future, by having more and more expensive interior contents, even the tiles, I always mention to my colleagues in Italy, you spend 100 euros per meter square of tiles. You don't spend 100 euros just to protect your structure. Why do that? You want nice room, you don't want nice structure? That's exactly what is shown here. And this really depends on the occupancy. We are here in the hotels. So even here, you see that nearly 70% goes on the non-structural component, windows, all the partition, and so on. So next generation should include not only the structure as primary focus, but include non-structural component, but more importantly on top of it, particularly for critical infrastructure, no building contents. That's very, very important for hospital, very, very important for nuclear power plant. And yes, that's very important because it's also based on the fact that hospital needs to be operative for nearly 3 days after a major event is occurring. Actually, they are designed for providing rescue operation after a major event, not only for being operative during a normal life. And other technologies that are available, for example, and this has been also promoted by UN, the United Nations Sustainable Development Goals, is early warning system. This is very important in the Caribbean region, for example. Coastal protection, evacuation, and so on, for a number of applications. It could be for petrochemical plant, it could be for hospitals that are not with the standards, compliance, and so on. And this can save also population because they can move, can be displaced on time when there is a warning that has been launched, for example. In Naples recently, I was there and I received an alert for Campi Flegrei, which is an area near Naples, in Pozzuoli area, where there is a bradisism, which is an earthquake going up and down, moving the level of water. And just an evacuation prevention where they send, for example, this alert at 12, just to check that that can be used during emergency. And that's something that has been implemented in Japan, for example, in other places around the world. And I'm pretty sure this has been implemented also here in some islands, because I was told by DPC, the civil protection, that this is also working very well as a sort of a test that has been carried out. Now, in terms of structural engineering, again, there are options that are available. For example, dissipation devices, as the one that you have in your car. If you go in a pothole, you don't feel all the vibration because there are dampers. So these dampers can be done on any type of material. Here, for example, shown in terms of friction at this connection that will dissipate energy while the system is moving. So it's damping the vibration induced on the pole or any lateral brace of the system. This is brass that can dissipate energy when it is bent laterally, and these shapes are used, for example, at the intersection between braces, so that when the system is moving laterally, these elements on top will dissipate energy, hence will control the lateral damage occurring. And this is part of, actually this was 22 years ago, when I studied this, not really this one, but starting from this idea of having a large mass on top of building. This is the Taipei 101 building that has a large mass sitting on top, tune mass damper, that will dissipate energy when there is a strong wind, when there is an earthquake, and when there is a gorilla hit that can hit the structure laterally. And because of that, the structure will not sense large vibration. Now, it can be not convenient to allocate large masses because you're losing rentable space. So what we designed at the time at Imperial is to have a multiple masses that are distributed along the height, so that by increasing the height of the building, you can tune them a different height. Hence, the building is going not to vibrate too much. And this is going to be more effective and convenient. Now, I'm concluding this with what I've been working on in the last 25 years, nearly, which is the consequence-based engineering, which is really what I think is the future of the codes. We are typically considering, and there's been discussion this morning, how we can characterize the seismic hazard, how we can characterize the wind hazard, how we can characterize, in general, the hazard event. Even microtremor, for example. In Dominican Republic, they are experiencing now a lot of vibration because of the new underground that has been built. But this is something that we have the tools. We know how to do it. Seismologists, engineers, they can do that. There is the physical damage. We have experience. I mean, we are learning how to design and how to assess structure. Now, all this part does not belong to our language. When you talk about vulnerability, social vulnerability, to most of engineers, they will say, oh, this is something that cannot be quantitatively defined. So they run away. This is not a good way to do that, because all this part you see here will influence the first part. This is last but not least, because the communities that are affected by dollars losses, this is what we are working now, all the losses that are induced by natural events is what is going to dictate the change in code of practice. Thank you very much.